So it's 12 o'clock. Probably more people here than I thought would be here on a rainy Friday before break, so that's kind of secret. Just before we get started for today, we'll pick up right where we left off last time. Are there any questions before we start today? No, looks like we're okay. Yep.
Did the assignment you did get moved to the 9th?
I did. I bumped the assignment a couple of days. I had one student with like a bunch of midterms and a bunch of other stuff due, and he asked for an extension, so a couple extra days for me is no big deal.
Did anyone tell you how good of a prof you are?
Oh my goodness, no, but thank you.
I treat us too good. Honest to God.
Actually, my husband and I, he works over in CIT Elevate teaching. We talked about how it's important just to recognize your students are kind of actual human beings and to treat people with a little bit of human respect, and maybe kind of life will work well from there. So it is one of my goals, and thank
We
you.
appreciate it.
Oh, now I'm going to be too flustered to do anything. Okay, so last day we finished up electric forces and vector additions. We got to talking about electric fields. We're going to use Coulomb's law in this expression to get an equation for our electric field. So we good to go? Are we ready? You good? Okay, so our goal is to think about a point charge and find the electric field around a point charge. We're going to do this based on the fact that we've already talked about Coulomb's law, knowing the force between two charges. We know that electric field is made by a source charge, so we're anticipating that the electric field is going to depend on the source charge. We're going to call our source charge positive Q. We're going to start with positive, we'll do negative on the next slide. Our goal is to find the electric field, which is a vector, at point P. Kind of one of the key parts to this approach is to remember that point P is just an empty point in space. There is nothing there, right? So P because I'm pointing at it. Okay? So nothing there, we're just pointing at it. So let's say that point P is a distance r, because we like to use r for distances, away from our charge Q, and our goal is to find an expression for the electric field vector at that point. The first step we do in this problem is we take a small positive test charge or probe charge and we place it at point P. So that's our next step in this process. So I will take a little positive charge Q and I will place it right here. Q is our test charge. It's small and it's positive. We almost always take test charges to be positive. So now what we do, the way we test it for an electric field, is we put that positive test charge there and we ask, does it feel an electric force? So we'll ask, does it feel an electric force? You see that we have two positive charges close together. Yes, it feels an electric force. And that force is repulsive. So let's draw that electric force. It pushes away. Are we okay to keep going? Good. So where our distance r away, we know that the force is repulsive, so we draw in the force. We know how to write down what that force is. It's given by Coulomb's law. The magnitude of the force is K times the magnitude of the test charge times the magnitude of the source charge divided by r squared. Our force is a vector, so to add the direction, we'll write the magnitude. We'll say that that force points away from Q. In Cartesian coordinates, you often give it in terms of x, y, and z, I, j, and k, right, left, up, down. It's more meaningful just to say that it points away, because that test charge we could have put anywhere, and away is very descriptive. Okay, so now we've got our force. To get to our electric field, we take away our test charge. So we remove our test charge Q. And we ask what's left behind. So we know that our electric field E is the force, the electric force vector, divided by the charge Q. That's how we established what electric field was. So if our test charge is positive, our force is away, then our electric field must be parallel to that. It must also point away. We take that force, we divide it by a positive number, we don't change the direction. So let's draw our electric field vector. It's going to point away. So we know that that points away from the charge Q. Okay, so good. Let's also find the magnitude. So the magnitude of the electric field is equal to the magnitude of the force, KQ times Q over R squared. And if we're finding the magnitude of field, we'll divide it by the magnitude of the test charge. We see here that the magnitude of the test charges cancel. Then that leaves us with an expression for our electric field. E has a magnitude of K times the magnitude of the source charge divided by the distance squared. The direction of our electric field vector is away from our positive source charge. Okay, so KQ over R squared for our electric field. Is this part okay? All right, so let's take this process, let's do it a tiny bit faster, let's apply it to a negative source charge. What will I say here? Sometimes people get into trouble because they mix up the equations for electric force and electric field. It might help to remember that your force is a force between two charges, so your force has both charges in it. An electric field is made by one charge, so that only has one charge in it. So it might help to remember those definitions as you're figuring out those equations.
One for the cheat sheet.
For your note sheet, not cheat sheet. Okay, so we've got our negative source charge, and we're going to try and find the electric field there. So we start the same way. We've got our negative source charge. We identify an empty point in space P. We place a small positive test charge at point P. So there's our plus Q. We ask, does it feel an electric force? It is going to feel a force. That force is going to be attractive. So there's the electric force between them. We can write down what that force is. F has a magnitude of K times the first charge times the second charge divided by R squared. And the direction of that force this time is towards. Okay? Towards because it's attractive. To find our electric field, we take away our test charge. And we ask what's left over. Well, our electric field E is equal to F divided by our test charge Q. So the electric field and the force are going to be parallel again. And our electric field is going to point towards the source charge. So the magnitude of our electric field E is equal to the magnitude of the force, K times Q times minus Q divided by R squared, magnitudes of all those divided by the magnitude of the test charge. And we're left with our electric field is K times the magnitude of the source charge divided by R squared, and the direction is towards. So a takeaway here is that electric field points away from a positive charge or out of positive, and it points in towards a negative charge. So that's going to be an important thing to remember. If you're stuck trying to remember what's the direction of the electric force, you can also, of the electric field, you can also remember it as the direction that a small positive test charge would move. So if you plunk down a little positive charge, whichever way that moves tells you the direction of the electric field. So that's another way to figure it out. Typical when we do these problems, we'll be calculating the magnitudes of the fields using this equation, and then we'll be looking at the source charge to figure out the direction. So we'll apply away or towards. Okay, premise okay? All right, we'll do some examples next. So let's go back to the hydrogen atom. In a hydrogen atom, a proton creates an electric field. Let's find the electric field at the electron, which is made by the proton. Okay, so this is kind of a pretty simple problem. We'll get a little bit more complex next. So we did do this problem before, and we found the electric force on the electron due to the proton, so we found that before. What's going on here is that the electron is like our test charge. That's the one that experienced the force that we found in a previous class. The proton is our source charge. That's the one that makes the field. You might read this problem and ask, doesn't the electron make an electric field? The answer to that question would be yes, it does, but this question doesn't ask for that. That'd be a valid question, find the electric field made by the electron, but it's not this question. Okay, so if you thought that, you'd be absolutely right. So let's find the electric field made by the proton. The magnitude of the electric field is going to be Coulomb's constant times the magnitude of the charge on a proton divided by r squared. When you do physics for a long time, radius of a hydrogen atom is kind of one of those things you tend to remember. 53 times 10 to the minus 12 meters. I would give you that on a formula sheet. You don't have to remember that. So let's, oh, and for our direction of electric field, you know it points away from a positive. So the direction of the electric field due to the proton at the electron is straight away from the electron. So there's the direction of that vector. So we've got 8.99 times 10 to the 9 newtons meters squared over Coulomb squared times 1.6 times 10 to the minus 19 coulombs divided by 53 times 10 to the minus 12 meters squared. So that is 5.12 times 10 to the 11 newtons per coulomb, and the direction is away from the proton. Any questions? Yeah?
I would think that the electron would be pulled toward the proton, so I don't understand why we're sending it in the opposite direction.
Okay, let's do part B of this question. Find the force on the electron. And let's see if this answers your question. So to find the force on this electron, let's remember the relationship between electric force and electric field. Force is equal to the charge, and this is the charge of the thing feeling the field, so that's the electron times the electric field. Charge on an electron is minus 1.6 times 10 to the minus 19 coulombs. Times the electric field, 5.12 times 10 to the 11 newtons per coulomb. This is negative. The electric field was pointed away. Because this is negative, it means force points towards. So if the test charge, the charge that feels the force, if that's negative, the field and the force are in opposite directions. Does that answer your question?
Yes. Would it also be okay if I thought about it like pretending that that electron was a positive test charge, and then it would be like the positive of the proton pushing, like repelling the positive of the test charge?
If you thought about that to get the direction of the field, no problem, because that is the direction of the field. If we placed a positive charge here, what direction would it move? Yeah, totally
Just the
valid.
direction.
Yeah, no problem. Okay, looks like we're good on that one, so let's get a little bit more complicated. We'll do a proper vector problem. Okay, so in the problem we're going to work on next, what I've got are two charges. One's positive, one's negative. They both have a size of 1 nanocoulomb, but one's positive and one's negative. Our task is to find the electric field at point P, and then part B is going to be find the force problem, but we'll deal with the electric field first. So just like when we did those finding the forces as a vector sum, I sort of had a list of steps that you should do. I wrote up the same steps for our electric field. It follows pretty much the same deal. So if we'd like to find the electric field at point P, we recognize that there are two charges making electric fields. We have two source charges, so we're going to get two electric fields, and we're going to want to do a vector sum of those. Our first step in our process is to draw the electric field vectors at point P. So everybody with your notes out, you should go ahead and draw those two vectors. If you're not taking notes today, maybe just try and draw them in your mind. Think of where you would put them. So take a second to do that, and then we'll look at what that's supposed to be like.
In this diagram, is the point P directly above the positive?
Yeah, it's right above Q1, straight in a line there. Or it's supposed to be. Maybe I got off a little bit. Yeah, it's not perfect. It's supposed to be right up the log. Okay, so let's just have a look at those vectors. So I did a slide like this before for fields. I'm going to do one for electric field. I did one before for forces. I'll do one for fields too. So the two most common ways to draw the electric field vectors wrong would be to, first of all, draw your electric field E1 on top of Q1. So you would draw E1 here. It's correct that it goes away, but you've drawn it on top of Q1. And for Q2 would be to draw it going into Q2. Okay, both of these would be wrong because they're not the electric field vectors at point P, right? These are the electric field vectors sort of right here. We want them up here. So you wouldn't draw them down there on those charges. The other way, which is not the worst thing in the world, but it's still not totally right, would be to draw E1 right here and to draw E2 right here. So that's also not quite right. So you shouldn't draw them with the tips of the arrow at point P. You should draw them with the tails of the vector at point P, because that's where your vector starts, is at the tails. So must draw with the tails at point P. Okay, so with that established, we'll go back and draw it on our diagram. So let's draw our vectors on this page. My electric field vector E1 is going to point straight up. Now that I've seen that point P is not straight above it, I can't label it. Point P is right there. Over there. Okay, that's better. So my electric field vector E1 points straight up. My electric field vector, because I'm going away from my positive charge, my electric field vector E2 is going to point towards my charge Q2. My vector E2, my two charges are the same magnitude, but this one is further away, so I drew that vector a little bit smaller. I'm trying to get it a little bit to scale here so I get the idea of what I'm doing. So there's our step one, draw the vectors. Step two is to find the magnitudes of those vectors. So let's do the magnitudes next. The magnitude of E1 is K times the magnitude of Q1 divided by R1 squared. R1 is the distance between the point, and my charge. So R1 is equal to 1 millimeter, or 1 times 10 to the minus 3 meters. So I've got 8.99 times 10 to the 9 newtons meters squared over coulombs squared, times 1 times 10 to the minus 9 coulombs, divided by 1 times 10 to the minus 3 meters, all squared. So the magnitude of my electric field E1 is 8.99 times 10 to the 6 newtons per coulomb. Okay, is that good? Next step in the process is to find the magnitude of the electric field vector E2. The magnitude of E2 is going to be K times the magnitude of Q2 divided by R2 squared. So I've got 8.99 times 10 to the 9 newtons meters squared over coulomb squared. The magnitude of charge Q2 means the positive value, 1 times 10 to the minus 9 coulombs, divided by R2 squared. I don't know my R2 just yet, but it does look like something I can find. So in my picture, R2 is going to be between my point and my charge. So from here to here is R2. That's the hypotenuse of a right angle triangle. So R2 is going to be the square root of 1 millimeter squared, plus this side squared, 1 millimeter plus 1 millimeter, 2 millimeters. So R2 has a value of 2.24 millimeters. I can put that in for my R2, 2.24 times 10 to the minus 3 meters squared. When it comes to units, because K has units of newtons times meters squared over coulombs squared, it means you should put your charge in coulombs and your distance in meters. You want all your units to line up here. So my magnitude of E2 is equal to 1.79 times 10 to the 6 newtons per coulomb. So now we've got step 1 done, we drew them. Step 2 is we found the magnitudes. Step 3 is we find the components. So now we're just finding components of a vector the usual way. So let's do the components of E1 first. Oh wait, I'll try and get everybody caught up first. Okay, so for my E1, my vector E1 points straight up. So these components are pretty straightforward. E1x is going to be 0. And we're taking positive x to be to the right and positive y to be up. E1y is positive because it points up, and it's the entire thing, 8.99 times 10 to the 6 newtons per coulomb. So the components of E1 are pretty straightforward. It's all in the y direction, so it only has a y component. E2, we'll have to go back to our trig. E2 points down and to the right. So the x component is to the right, E2x. Our y component is down, E2y. If we want to be able to find the components of E2, we're going to have to find that angle theta, so we're back to our geometry. So I've labeled my angle theta relative to the horizontal right here. If this angle is theta, then this angle is theta. One of those math things, two parallel lines cut through with a z, the inside angles have to be the same. So if I want to find my theta, I recognize that for this angle I know the opposite and the adjacent. I can use tan to find my angle theta. So tan theta is the opposite, 1 millimeter, divided by the adjacent, which is 2 millimeters, 1 millimeter over 2 millimeters is 0.5, so theta is the inverse tan of 0.5. So theta is equal to 26.6 degrees. Okay. Now that I know theta, I can find my components. So my x component, E2x, is adjacent to my angle. So I'm going to use cosine E2 times cosine theta. E2, I did find that value, 1.79 times 10 to the 6. Multiply that by cosine 26.6 degrees. And what I get for my x component of E2 is 1.60 times 10 to the 6 newtons per coulomb. So there's my x component of E2. Y component will go with the same idea. E2y points down, so it's negative. The y component is opposite the angle, so we use sine theta. So we've got negative 1.79 times 10 to the 6 newtons per coulomb times sine of 26.6 degrees. So our y component is negative 0.80 times 10 to the 6 newtons per coulomb. Questions there? Okay, so this is basic vector stuff that you probably covered for a long time in 1050 or 1020. To find our vector sum, that's our next bit. We take the vector sum to find the net field. So for our vector sum, we add up the x components. So the sum of the x components is E1x plus E2x. Fill in our values there. So the x component is only due to E2. For our y components, we fill in our y components. 8.99 times 10 to the 6 newtons per coulomb minus 0.8 times 10 to the 6 newtons per coulomb. That gives us a y component of 8.19 times 10 to the 6 newtons per coulomb. So there are the x and y components of the electric field vector. To finish the problem, you do have to write it as a vector. So we say E is the x component, 1.6 in the x direction, plus the y component, 8.19 in the y component, times 10 to the 6 newtons per coulomb. Any questions? Some people prefer the polar notation of vectors to find the magnitude and the angle. If you prefer to take your components and go to polar notation, that's no problem. If you like that better, it's just as right as unit vector notation. Okay, part B of this problem. Find the force on a proton if it is placed at point B. So that's a good part B of this question, and you'll probably find that whenever you have this kind of a question on the test, either part A is going to be find the field and part B is find the force, or part A is find the force and part B is find the field. So force and field almost always go together in these questions. If you want to find the force, there are two ways to do it. You can go at it the long way. And the long way would be the vector addition, like we did last time. So you would do KQ1, Q2 over R squared for both of them, find the magnitudes, find the components, do the vector addition. That's going to take you a long time. And then there's the short way. This is the way I recommend, which is you remember force is equal to charge times electric field. So we put a proton at point P, so we put in the charge of a proton, 1.6 times 10 to the minus 19 coulombs. Multiply it by the field, 1.6 I hat plus 8.19 J hat times 10 to the 6 newtons per coulomb. And we get our force as 2.56 I plus 13.1 J times 10 to the minus 13 newtons. Okay, so if you go the short way, it's a one-liner. If you go the long way, it's probably a one-pager. Okay, questions? Alright, so I think it's probably pretty boring for you guys to watch me solve these. I've got a couple of worked out ones that I'll post in with the notes. Probably a good idea for you to work through those just to make sure you got the idea. So now we're going to come to the next part of the course. Historically, and if you did Physics 1051 a couple years back, here's where you'll see a change in the course. We don't only have point charges, right? We don't just have protons and electrons sitting around being charges. We also have solid objects that carry charge. So you can have disks of charge and planes, spheres, wires especially, right? We've got lots of charge running through wires. Anything that has a charge makes an electric field. So these continuous distributions, these big solid objects in 2 and 3 dimensions, they have charge, so they make electric fields. You can find those fields using calculus, doing the integrals. We're going to steer away from that a little bit because it's not that important. It's not one of the outcomes of this class. So what I'm going to do is set the stage for how you apply that idea to find the electric field. I'll give you some of the primary results, and then we'll go on to use the results. If you're interested in getting into the calculus, then you might like Physics 2055, which will be offered in the winter term. So, to get the idea of how you find the electric field of a continuous charge distribution, let's say we started with a system of 7 different point charges. Okay, so we just did a system of 2 charges. You could just as well have 7 charges. If we wanted to find the electric field at point P due to those 7 charges, we would follow the method we just did. So we would draw the electric field due to charge 1. Due to charge 1 points down this way. Then we might draw the electric field due to charge 7. 7 points up this way. Then we could do 2 and 6. So electric field 2 will point down this way. Electric field 6 will point up this way. And we can do 3 and 5. So 3 comes this way. 5 comes this way. And then we can also do the electric field due to charge 4 comes out this way. So if we did this, we draw each of our vectors. We would then add up we would find each individual electric field magnitude, K times Q over R squared. And I put the I on it to tell us we do this for each one of them. So we do 1 first, then 2, then 3, then 4, and so on. Then we find the net X component by adding up all the X components. We find the net Y component by adding up all the Y components. At this point in this process, you might look at this picture and think, don't the Y components cancel due to symmetry? We have just as many up as we have down. If you thought that, you would be absolutely right, and that's what you'd find for this answer. And then ultimately, we would write our electric field as a vector with an X component and a Y component. Okay, so this is if we were going to do it with 7 individual point charges. The way we get to our lines of charge and bodies of charge is that we take these charges and we push them closer together. So let's push the charges QI close together. If we take those 7 charges and we push them close together, we're seeing something that looks a little bit like a wire, but it's really kind of lumpy. You can see kind of the circles of the charges. So if we want to get it so it looks like a solid cylinder, like a wire, what we have to do is instead of having 7 charges, we need 1 trillion charges. We need lots and lots of very small charges. So what we do to get our line of charge is we push many small charges very close together. So the difference now between this setup and this setup, it's not really just notation, it's kind of in theory as well, but let's talk about the notation. So in this picture we have individual charges Qi. In this picture we have many small charges. They're very teeny tiny, and when we have very small things, we call it dq. So this is a calculus thing. If you have a very small piece of something, an element of something, you call it d with your variable. So dq go together to tell us a very small portion of charge. For this one, we would say that EI, the electric field due to the little charge, is K times Qi over R squared. For this one, we would say this little charge makes them a little electric field, K times dq over R squared. Okay. Because it's a little field, we call it dE. For my x component, on the left, we add up the x's. On the right, we still add them up, but when you're adding together many small things pushed together like that, we're not doing a sum anymore, now we're doing an integral. So here's the difference, is this is where the calculus comes in. So when you add together a bunch of small things, it goes from a sum to an integral. Likewise with the y component, EY is the sum or the integral of the y components. And then in the end, we still write our electric field as a vector. We're not going to apply these integrals to lines of charges, but we are coming back to this idea when we get into flux in the next chapter to adding up a bunch of small things, and we'll do some integrals then. Okay with the idea? This is probably something you've seen in Math 1001 by now. Like we're 5 weeks in, you would have started integration by now, right? Yes, okay. But I don't know if they give it a physical sense like this or not. It's a long time since I did Math 1001. So in Physics 1051, we talk a lot about capacitors. We're going to get into some circuit analysis in later chapters. So we're going to start with the idea of capacitors, and to get there we have to begin with planes of charge, so solid planes of charge. So a solid plane of charge is just a solid object. What is the electric field around an infinitely charged plane? So an infinitely charged plane means it's a two-dimensional object, so it's thin and flat. It's infinite in 2 dimensions. So I'll put on a coordinate system where x is to the right, z is out of the page, and y is up. So it's infinite in x and z. And it's thin in the y direction. This infinitely charged plane does have a charge, but when we're talking about big solid objects, it makes more sense to talk about charge density instead of total charge. So this plane is going to have surface charge density, and sometimes we call it surface area charge density. It has a symbol of the Greek letter sigma, and it's the total charge divided by the total area. So that's charge. That's area. So then sigma has units of coulombs over meters squared. And this is the kind of charge density we use for a plane. Okay, still good? So we could have a plane, let's say it's filled with positive charges. So in a 3D drawing, it would look something like this. In an edge-on drawing, it might look like this. So our plane is full of charge. Because it's full of charge, it's going to make electric fields, because all those charges make electric fields. The way we find the electric fields is we write down the expression for the field due to each little individual teeny tiny charge, and we add it up by doing the integral over the entire object. It's kind of a complicated integral. I'm not sure if your book does it or not right from scratch. What we see as we do the integral, let's look at the edge view. So let's say we wanted to find the electric field right here. This charge would make an electric field that points away. This charge would make an electric field that points away. And this charge would make an electric field that points straight up. So that's what some of those constituent electric fields would look like. What we see happening is that the horizontal components cancel. So X and Z cancel. We're left with Y, and the Y component is constant. So that's the result we get for electric field around a plane. Why don't we try and draw some of those electric field vectors? So if our Y component is constant, the electric field around a plane looks like this. Comes straight out of the positive, and will go straight into a negative. Something like that. So that's kind of what your electric field looks like. So our electric field equals constant and perpendicular to plane. The value of the electric field is the charge density sigma divided by 2 times epsilon naught, where epsilon naught was the permittivity of free space, 8.85 times 10 to the minus 12 coulombs squared over Newton's meters squared. And the direction of the electric field would be away from positive or towards negative. Okay, so there's one result that we're going to use quite a lot.
Can you explain more the away from positive towards negative? Because, like,
Maybe I needed to word now.
we wrote arrows, or,
Yeah.
okay.
So if this was a positive plane, it'd look like this.
That's
Negative.
what I was wondering, because we had arrows
Yeah.
on both sides, okay.
If you're looking at the downloaded notes, the next slide is just a picture I stole from your book, so it's just a nicer version of what I drew here. So let's put it together, and we'll talk about a capacitor. A capacitor is an electrical device that we get, and we get that when we put 2 planes together. So to start with what a capacitor looks like, anytime you take something apart, something electronic, it's going to look something like this. So they'll have circuit boards inside. Put it up on the screen if it's harder to see. So there's a circuit board. I just asked John to grab me something out of a computer. So the something he got me was a video card.
That's an old graphics card.
Pardon?
That's an old graphics card.
Oh yeah, it's really old. He gave me this years ago. So these little round things here, those are all capacitors. Here's a bigger one, and I got this from one of the second-year labs. We're going to talk about planes for a while. In practice, they're actually made round. Capacitors are devices. You use them in circuits, and you use them to store electric energy. We're going to talk about that when we get to the capacitors chapter. If you ever start tinkering with stuff, like your TV, computer, all this stuff, there's a sticker on the back that says do not open, right? That sticker is not just there for warranty purposes. So after you plug in your computer and your TV, all of these little capacitors, they charge up. They store lots and lots and lots of energy. After you unplug your TV, those capacitors are still charged. They still have the energy. So if you unplug your TV and you're working on it in the back and you put a screwdriver into a capacitor, you can get a very big shock. That's why you're not supposed to open these things. So there's that. So now let's have a look at our capacitor. This is a simplistic view. We take two planes. One of them is going to have positive charge and one of them is going to have negative charge, and we're going to place them close together. So let's say that this one has the positive charge, this one has the negative charge. And I'll draw some pluses and minuses on there. And then we can have a side view as well. We know that each plate has area A, and the charge density is the total charge divided by the total area. And you can figure those things out from the geometry. We might ask to find what is the electric field near the plates of those two things. So if we wanted to find the electric field, I'm going to call this plate 1 and this plate 2. If I wanted to find the total electric field, I would have to find the field due to plate 1, add it to the field due to plate 2. So that's going to be the strategy. Let's take a two-dimensional view. Here's plate 1, here's plate 2. This is our positive, and this is our negative. So let's look at each part there. So let's start out here on this side. So at this point right here, what's the direction of the electric field due to plate 1? To the right or to the left? To the left, because we go away from the positive. Here's my electric field E1. I'm going to take positive x to be to the right, positive y to be up. The magnitude of the field was sigma over 2 epsilon naught. It points left, so it's minus I hat. Okay, let's put in my second electric field as well.
Just wanted to focus.
I didn't like that at all. Okay, what's the direction of the electric field right here due to plate 2, right or left? Right, because it goes in towards the negative. There's my E2. It has a value of sigma over 2 epsilon naught I hat. So my net electric field right here is E1 plus E2 equals 0. So outside of the plate of the capacitor, the electric field is 0. Let's do inside. So at a spot inside, my electric field due to plate 1 points away. There's E1, sigma over 2 epsilon naught I hat. My electric field due to plate 2 also points to the right because it's in towards the negative. E2 is sigma over 2 epsilon naught I hat. So then my total electric field in there
Is
sigma over epsilon naught I hat. Okay? Those two things added together. Okay, last one, and we'll write this down really quickly. My electric field out to the right of plate 2 points away from plate 1. So E1 equals epsilon over 2, sigma over 2 epsilon naught I hat is my E1. E2 is to the left. E2 is negative sigma over 2 epsilon naught I hat. So my net electric field E is E1 plus E2 equals 0. So the takeaway is that the electric field outside a capacitor is 0. In between the plates, it's sigma over epsilon naught. Okay, that takes us right up to time, so we'll quit there. And then we're back after break. I hope you all have a nice break and come back all refreshed.